So in this video, I'm going to be doing a crypto challenge from the Cyber Apocalypse CTF 2022. I'm going to be doing the Down the Rabin Hole challenge. Here is the info if you want it. And basically the cliffs for this challenge is just maths. That's kind of all we're going to use. So we have the source code. So if we take a look at that, basically what's going on is we have a random 128-bit prime as our coefficient, and we are taking half the flag as a message. We're inputting that into an encryption function, and then we're going to output those variables. We see here that the P and the Q is the product, or P and Q are primes from this get primes function, which if we look at it is basically just taking that coefficient and multiplying it by 3, and then multiplying it again by a random 512-bit prime, adding 2 to it, checking if it's prime, and if it is, finally going along. So basically P and Q are going to be primes of that form. And then what we're doing is padding the message, kind of doing this formula here, and then outputting these variables. So what I want to show is if we look at how P and Q are made, so P is equal to 3 times, let's just capital P sub 1 for just some random 512-bit prime, times the coefficient, which we know is 128 bits. Q is the same thing. It's a different 512-bit prime. And then we know N is the product of P and Q. Well, we can kind of figure out the order of what N is because we know that the coefficient is 128 bits. We're multiplying it by a number that is 512 bits. We're multiplying it by 3, which is 2 bits. So we know that that is, what is that, 642 bits. Same for Q. And then we know then that N is going to be 1284 bits. Well, the reason that's important is because if we look here, we see that the half the flag, we're going to pad it. For a padded message, we're padding it to 64 bytes, which means the message is smaller than 64 bytes. But even if we go by it being 64 bytes, which is 512 bits, we're taking this 512-bit number and adding a 128-bit number to it. So it's just some number still less than 513 bits. Multiplying it by a 512-bit number, which means this here is only going to be 1024-ish bits, which is smaller than our modulus, which we showed was 1284 bits. So we're not actually, we never, wrapped around the modulus, so we can essentially just ignore that, and this, we're basically working on this formula here over the entire integers instead of the integers modulo some number. And if we take what that is, so we have our, say like C1 is equal to M1 times M1, what was it, plus the coefficient. That's basically just a quadratic equation, m1 squared plus the coefficient sub 1 minus c1 equals 0. So since we're working over the integers, we can actually, if we knew what coefficient was, we could just solve this equation with the quadratic formula, essentially. So how do we get the coefficient? Well, we know if we look at how N is made, right? It is P times Q. So 3 times some number we don't know. Let's just call that number X, right? So that's X times the coefficient plus 2. And Q is 3 times some other big number we don't know. Let's just call that Y times the coefficient plus 2. And so n is the product of these two numbers, so we can just FOIL this out, and we get xy coefficient squared plus 2x coefficient plus 2y times the coefficient plus 4 is equal to n. If we just subtract 4 from both sides of this equation, we get n minus 4. And then if we look here at every term on the left-hand side of this equation has a factor of coefficient in it. And so there's a theorem in number theory that says if we have the sum of a bunch of numbers and every one of those numbers has a factor of a number in it, then the result is also has a factor of that number. So we know that n minus 4 is divisible by the coefficient. It has the factor coefficient in it. Well, we have n1 and n2, right? We have another one that was calculated the same way. I mean, different P1 and P2 values, but what essentially then we could take the GCD of n1 minus 4 and then with n2 minus 4, and whatever that answer is going to be some multiple of the coefficient. Like we know it'll at least have a 3 in it. I'm not sure. It could maybe have another number in it, but basically the way it works is if it is some multiple of coefficient, it's going to be a small multiple of coefficient. So we can just factor whatever we get here, and the big number we're going to be left with is the coefficient. So if we know the coefficient, we can just plug it in there and solve that equation for m. So let's just actually go ahead and do that. So if we take these numbers, right, this was our n1, this is C1. We don't even need this because this was the padded message that we actually don't even care about. We could use either one, but we're just going to use the smaller one. And then I just remembered off my head. So what we want to do then is take. So I'm going to use SymPy to get the GCD, which is just a Python package. But you can use whatever you want to get the GCD. And then since I'm using SymPy, I'll also use that to solve the quadratic. But again, we could have just done this in the terminal and used like Wolfram Alpha, or I'm just doing it this way because I have SymPy on my computer, so it's easier. And then so we want to take the GCD of n1 minus 4 and n2 minus 4. And then, like I said, we know that it'll at least have factor 3, but any factors it's going to have is going to be small factors. So let's just go ahead and do it doesn't matter, it'll be super fast. So that basically is just going to factor out any small factors from that. So what we're going to be left with is the actual coefficient. And then we can just solve that quadratic equation just using SymPy. I'm going to tell it x is the variable we're using, and then let's just do plus coefficient minus C1, and we're doing that over X. And we know the flag is, so I think SymPy returns it as like its own like integer class thing. So I'm converting it to Python int, and we're going to convert that to bytes, and it's going to give us two roots, right? The negative and positive root, because there's two roots for the quadratic, and I believe it negative and then positive, so we'll do the second root, and then basically just repeat this, but now we will do it for C2, and we will add that to the flag, and then we should just be able to print out the flag. Oh, I do want to I can't remember if it's numbers or numbers. I think it's just number. And that should give us the answer. And there we go. That's our flag. So I do know that the challenge was supposed to be based on the Rabin crypto system, but the flag itself was too small for the modulus. So this kind of would be an unintended solution, but sort of the most straightforward, direct way. Otherwise, then you'd want to use like the Franklin reader. I don't know how to say it. Related message attack on the padding, but I don't know. This is just a much easier video to make. So hopefully all that made sense. If you have any questions, feel free to ask. If you made it all the way through this video, thanks for watching. And yeah, take care.